Now we will basically see two methods that exactly follow this downward closure property cluster criterion and use bottom-up search, a priori style bottom-up search for subspaces or subspace clusters. Actually this typically holds only for these density-based clustering approaches, so it's not a big surprise that we'll see one method which is exactly based on this cluster model, grid-based cluster model, which is called clique, and the second method takes the dbScan model, the density-based model from dbScan, computes a bottom-up subspace, density-based subspace clustering search with this cluster model, and that is called subclu, the method. And then later on we'll see two other examples where the cluster model does not really implement the downward closure property. In that case we'll see that there are other heuristics employed in order to find subspaces, but still those methods start with one-dimensional subspace clusters and then try to somehow expand them by merging them, and we'll see how that actually works. But we start with these two density-based models that actually follow this downward closure property. And as promised, the first one called clique is historically probably also the first bottom-up subspace clustering algorithm, and that uses exactly the density-based model, the grid-based density-based model that we just saw here. Yeah? So we define intervals, one-dimensional intervals, and the intersection of these one-dimensional intervals form higher dimensional volumes, and then we just say that if enough points are in those volumes here, so m is one input parameter, and the side length of these intervals is the second parameter, then these grid cells are dense enough to form a cluster, to be in a dense area. Okay, so yeah, clusters are dense regions in the feature space. So we put, so that is the second parameter. Sorry, that is the parameter that specifies the volume, which is xi here in this algorithm, and xi actually is the number of partitions per feature space, per feature. Yeah, sorry. That means we partition the feature space or the feature, each feature in xi equal sized parts. So we see here we have the salary feature, and the feature is divided into 10 partitions, 10 intervals, and the same holds true for age. The feature, the second feature age here, is also partitioned into 10 intervals, and all the intervals have the same side length. Yeah. And now, as we said before, a unit is an intersection of one interval from each dimension. So if we only have a two-dimensional space with age as one feature and salary as the second feature, a two-dimensional unit would be an intersection of any interval along age and any interval along salary. So for example, for this gray shaded thing here called U here, yeah, this is obviously the intersection of this interval here, 30 to 35 along age, and this is times 1,000, so 1,000 to 2,000 along salary. Yeah? So this and this, these two intervals intersect here, and we get this unit here, this grid cell, and we call the grid cell units in that case. Yeah? And so that is the first parameter, the number of grid cell of intervals according along each feature, yeah, giving you the volume actually, and then we need this minimum of points to be which need to be in a unit, so that the unit is dense, considered to be dense, considered to be a cluster or part of the cluster, and that is the m of this one here. So in this paper here, in this method, it is called tau. Yeah, that is the minimum number of points that need to be in one unit. So a dense a unit is dense if it contains more than tau points. Yeah, so we have these two input parameters, one specifying the volume, one specifying the minimum number of points in the volume. So the dense grid cells are in the middle of a cluster. So and maybe there are neighboring dense grid cells. So clusters are defined as maximum sets of connected dense units. Yeah. So for example, here we have one big soup, one big set of neighboring grid cells, and this is considered to be a cluster. Yeah. So that is a general idea, and now we can apply, since we already know here from this one here that this cluster model is actually monotonic, so it implements the downward closure property. So we know if U is dense, we know that also the one-dimensional intervals need to be dense, yeah, or the other way around. So for example, if this one here is not dense, then we know that all the combinations of this interval with all the other intervals from H doesn't make sense, because we won't get any dense two-dimensional grid cell. Yeah? So that is used here for a bottom-up a priori search. And basically, clique is a two-step approach, because in the first step, we actually try to expand or find those dense units, yeah, starting from one-dimensional dense units to form higher dimensional dense units. And when this is done, actually, we do the final clustering by just computing all the connected dense units. Yeah? So we first of all just connect all the individual units which are dense in each subspace, and then afterwards each subspace is so to say post-processed to form the final clusters by just connecting the neighboring dense grid cells, dense units. Yeah? So first step is the subspace search, and that is, as I said before, implemented or based on the downward closure property of dense grid cells. So we can employ this kind of a priori branch and bound search. And the most important or the most interesting part maybe is the candidate generation. Yeah? So we have a set of k-1 dimensional dense units, and from those dense units we know that only those dense units can form, so they are k-1 dimensional, only those dense units can form k-dimensional dense units, yeah, because of their downward closure property. So we generate the candidate set of k-dimensional dense units. Need not to be all of those candidates actually dense, but at least those are the candidate sets by just self-joining the sets of dense units that are k-1 dimensional. Yeah? So we have already 5-dimensional dense grid cells. Yeah? We already know that which 5-dimensional grid cells are dense, and now we want to generate the candidate 6-dimensional units that can be dense. We still need to test them, but they can be, which can be dense. Yeah. So what we actually do is we take all the 5-dimensional ones and join them. Yeah. And the join condition is they need to be similar in the first 4 dimensions. Yeah. So the 5th dimension could be anything, but if they have the same first 4 dimensions, we join them. And the join is obviously the first 4 plus the 2 that are missing, so to say. Yeah? So that is the candidate generation, the self-join of the dense, the k-1 dimensional grid cells, 5-dimensional grid cells, to form the k-dimensional candidates, 6-dimensional candidates in that case. Yeah? So once again, the join condition, units share the first k-2 dimensions. Yeah, so we look at the k-1 dimensional dense units and join them if they have the first k-2 dimensions in common. Yeah, so k-1 in our example was 5, k-2 is 4, so they need to have the 4 first dimensions in common. Yeah? And so we do that with the join, and then after the join we can even disregard those candidates which have a k-1 dimensional projection which is not included in the set of k-1 dimensional dense units, yeah, that we already know, of course. And for the remaining candidates we still have to check the density, because it may be that they are not dense anymore, but at least they can be. Yeah? So that is the candidate generation, which is pretty much the same as in the a priori frequent item set mining problem. If you recall, so we have the k minus 1 dimensional, or the item sets with k minus 1 items, and we join them, and which are frequent, and we join them by with the same join condition actually. So they need to have the first k minus 2 items in common, and then we join them to form the candidates of length k. And that's the same here basically.